Hello there, my name is Alec Yip, and this is my thesis defense on rim-mounted reconfigurable surfaces for interference nulling and focus-fed asymmetric reflector antenna systems, with committee members Dr. Stephen Ellingson, Dr. R. Michael Beer, and Dr. Bradley Davis. So before we begin, I'd like to thank the National Science Foundation for funding this project with the NSF grant listed below. So before we even begin with the thesis, we need to talk about the background and motivation. Why are we doing this, and where does this work come from? So this work is entirely aimed at radio astronomy, and so radio astronomy is the study of astronomical phenomena using electromagnetic signals in the radio microwave frequency bands. So, however, man-made objects like low Earth orbit satellites may transmit in the same frequency bands that radio astronomers use, thereby causing interference. So the objective of many engineers and radio astronomers alike is to determine methods to mitigate this interference for these reflector systems. One of the solutions was to use a phased array feed. So the phased array feed was able to electronically control the phasing on the array feed to the reflector, thereby causing a null in the desired direction of the interferer. This has advantages in that it can drive a null. However, the disadvantage is that it had led to a dynamic main lobe variability. So in lieu of this, there have been other solutions attempted to mitigate this interference, and one of the more recent ones was to use an electronic reconfigurable surface. So in 2021, a paper was written that conceptualized the ERS and showed the feasibility, at least in the preliminary stages. So the ERS was conceptualized as a reflector array that attaches to a surface extending the original paraboloid. In other words, it's conformal to a paraboloid, rather. And so these elements were realized as patch antennas, although that's not necessarily the case. That's not necessarily important. And so this was analyzed using physical optics. The method of physical optics, we're using 2N cross H to determine the equivalent surface current densities on the reflector surface. So this now spawned the idea to conduct further research on this topic. And one of the first things to do was determine whether or not this physical optics approximation was accurate. So one of the first things needed for the physical optics approximation is that the surface be electrically large compared to the wavelength. However, for the main reflector for main reflectors of sufficiently large diameter, this is relatively accurate the first couple side lobes. However, the ERS now it was actually the elements themselves on the order of a wavelength, which violates one of the first principles of physical optics. However, shown in this paper in 2023 that the approximations are relatively close to one another within the first couple side lobes. So that means that physical optics could be used to analyze the system. The second of which was to create algorithms to constrain the main lobe. So what happened was when preliminary algorithms were done to set the states of the ERS, the main lobe gain did change a little bit. And so with this paper here in 2023, there have been methods to set the states of the ERS such that the main lobe gain stays constant, as well as a null is driven in a particular direction. Lastly, a physical model was introduced to determine if it would have significant impact on the radiation pattern. So this physical model was done for each of the ERS elements to account for the switching losses and to account for the dielectric losses. And it was found that the radiation efficiency of the reflector system did not change that much. So with this in mind, we now augment the prior research by first deriving a closed form expression for the minimum width of the ERS to null a particular side lobe. This would minimize the material necessary for the reflector system. The second of which is to analyze ERS implementations that are not conformal, in particular, whether the implementations that are rectangular flat panels, so which ERS elements lie on. We'll call them outricker panels. So these flat panels would be easier to build than a conformal implementation that attaches to the original reflector. So now the results here from the thesis was that we were able to derive an approximate closed form expression for the minimum width of the ERS to null a particular side lobe, and we analyzed 4 flat ERS implementations. And they're on the screen right here, these 4 implementations, the front and side view. And we discussed the trade-offs for each implementation in terms of the cross-pole, the main lobe directivity, null depth, so on and so forth. So before we can even delve into deriving the expression for the minimum width, we want to talk about the geometry and how we're going to analyze these systems. So at least for the conformal ERS implementation, and also the non-conformal ERS implementation as well, the fixed reflector will always be constant. It will be an 18-meter reflector, i.e. 90 lambda at 1.5 gigahertz with an F/d of 0.4. So for the conformal ERS implementation, we assume that it occupies the rim width W perpendicular, where W perpendicular is that projected width, and we assume that each element has dimensions lambda by 2 by lambda by 2. So they're square. And so now we talk about, now the geometry is defined, we want to talk about how we're going to determine the skytoelectric field. So for the fixed proportional reflector, this is relatively simple. We use a physical optics approximation using 2n cross h to determine the equivalent surface current densities and use the radiation integrals to determine the skytoelectric field. Extending this idea to the ERS, the equivalent surface current density on each of the elements or cells, if you will, in the process of evaluating the skytoelectric field is 2n cross h, where h is an incident magnetic field, now multiplied by this Cn value, where Cn is the reconfigurability factor. So in principle, Cn can be any value we want. However, we restrict our analysis to unit modulus. Cn values are unit modulus, meaning that they have magnitude of 1, and that we can only phase shift the reflected field from each of the elements. So, because there are a discrete number of ERS elements on the reflector, the skytoelectric field, the skytoelectric field is no longer an integral, rather it's a summation, and that expression is here on screen. So the last question to ask before we begin with the analysis is how we're going to set these Cn values. So we elect to choose a rudimentary way to set these element states, which is the serial search algorithm, abbreviated SSA. So this equation here for the skytoelectric field from the ERS is summed one at a time such that the copolarized electric field in the direction of the desired null, the interferer, is minimized for the entire reflector system. So there are other algorithms that exist. This is a simple algorithm we can use to analyze the reflector system. So now we can apply this theory and to an example. So we want to null the second side lobe of the unmodified reflector, a 90 lambda diameter reflector with 0.4 F/d at 1.5 gigahertz, with 1-bit phase control for the Cn values. In other words, the Cn values are either +1 or -1, corresponding to 0-degree phase shift or 180-degree phase shift, respectively. And we note that, there's the feed used for the system is going to be a Huygens source feed with a raised cosine Q model. So where Q is chosen such that the edge illumination from the vertex to the rim of the reflector is going to be -11 dB, which leads to optimal edge illumination. So after doing the serial search algorithm, I plotted the values on a diagram and color-coded them for visual representation. So on the right, we see that there are contiguous areas of red and blue, so +1 and -1, and these indicate the element states for the Cn values. So with these Cn values determined, we can now determine the scattered electric field from the reflector system, and so which is on the screen on the left here. So the black dashed line indicates the original 18-meter pattern, where the second side lobe occurs at 1.75 degrees from boresight, and this is done in the H-plane. So we see here that a deep null can be driven in that desired direction. So this example is important because now it will serve as a baseline for comparison for the examples later on in this thesis. So now we can delve into the minimizing the width of the ERS. So at the end of the day, what we want to do is we want to have a closed form solution for the minimum width needed to null a side lobe. This means that we have to determine a closed form expression for the scattered electric field from the fixed portion reflector and a scattered electric field from the ERS. So what we're going to do is we're going to equate those two expressions equal to one another, and we're going to solve for the value of W, the W perpendicular needed to cancel that particular side lobe in that direction. So the first thing that we have to do is determine the scattered electric field from the fixed portion of the reflector. So there are many ways to do this. One of the ways that we like to do is to use aperture theory, in particular circular aperture theory. The advantage is that circular aperture theory have a closed form solution, and the models are relatively accurate to a regular reflector, as shown in previous research. So now the question becomes, what model do we use to select to model the skyline electric field from the reflector? And we choose the parabolic on the pedestal model, which is given by little f of theta, and where big F of theta n is the pattern function. So much of the work in prior research has been done to solve for this value n, such that it approximates the skyline-electric field from the reflector. And after solving for n, given these parameters, we can determine the skyline-electric field is on the screen right here. So we know that this is for a y-polarized aperture electric field. It's the same as our source on the prior slide. So we have the approximate closed form expression for the skyline-electric field from the fixed portion of the reflector. Now we need to find the skyline-electric field from the ERS, at least in closed form. So that becomes a little more tricky because the ERS from the electric field from the ERS is now the electric field from an array. And that array magnitude might change over a certain direction from Borside, where Borside is at phase equals 0 degrees. So going forth in this derivation, we assume one thing, is that the elements on the ERS can now perfectly phase shift. In other words, we can have a perfectly phase shifting array that can produce a maximum magnitude in any direction, which means that the magnitude over a certain direction, at least close to the main lobe, is relatively constant. So if it's relatively constant at, say, 2 degrees from Borside, it's going to be the same value at the maximum magnitude at 0 degrees from Borside, or at Borside rather. And with this approximation, we can say any direction here we choose in a particular, the ERS magnitude in any direction is going to be the same magnitude at phase equals 0. So why do we choose phase equals 0? Well, because the expressions for circular aperture theory are all centered on 0. In other words, the maximum magnitude is at 0, and we can use those expressions on the prior slide. And so by doing so, we can develop this expression here in kind of maroonish red that gives us the approximate scatter electric field from the ERS, given that the elements are perfectly phase shifted, in other words, continuous phase variation across all the elements. And we see here that it's relatively similar to the expression on the prior slide, with this only difference in this factor where A0 plus minus A is now the projected rim area of the ERS. So, as stated in the beginning, that we want to equate the two closed form expressions equal to one another, and we can solve for the minimum width of the ERS needed. And by doing some manipulation, we arrive at the final result here, which states that based on the diameter of the reflector and the pattern function, we can determine what the minimum width needed is. So we have this expression now, and we want to determine, is this accurate, or does this make sense? So the first thing we're going to do is we're going to evaluate the two extremes of this function. When the magnitude of the pattern function goes to 1, so when the magnitude of the pattern function goes to 1, that means that we are looking at the Borside. So in other words, we want this equation, equation 4.30, should yield us a rim area that is equal to the area of the reflector. Because if we want to cancel the main lobe, aperture theory tells us that we have to have a projected area that's as equally as big as the original reflector to cancel it out. So by substituting f equals 1 into the equation, we get W perpendicular minimum is d times rad 2 minus 1 over 2, which leads to a rim area of pi times d over 2 squared, which is the area of the fixed portion of the reflector. So that checks out. And the second condition to check is when we're at a null. In other words, magnitude f goes to 0. When magnitude f goes to 0, means that we do not have anything to cancel, therefore W perpendicular min should be equal to 0. In which this case, W perpendicular min using equation 4.30 does equal 0. So those two extremes do check out. And so now we want to see, does this work using physical optics as we did in the prior example? So as discussed earlier, we're going to use the same system parameters, d equals 18, f over d 0.4, and q is equal to 1.4, which edge illumination minus 11 dB. So on the far left column in the table below, we see m equals 1, 2, and 3. This indicates the first, second, and third side lobe of the unmodified reflector pattern. So in the second column, we see this W perpendicular minimum, calculate using this equation here, 4.30. And so now we can talk about the physical optics. So physical optics was done by trial and error to determine the minimum width needed to cancel a side lobe. So we see here for continuous phase, 2-bit continuous phase, which means that we can perfectly beamform any direction, we see that it closely matches W perpendicular min calculated from 4.30, which makes sense because we made the assumption that the elements can perfectly phase shift. However, for 2-bit and 1-bit, using a serial search algorithm, the actual widths needed to cancel the side lobes are actually much higher. So why is this the case? So we note that I plotted an example here on the right to show the reason why. So for a rim width of 1.2 meters, I plotted the magnitude of electric fields, the normalized magnitude of electric fields over a certain range of theta. So we see here for continuous phase variation, it's constant, as we assumed. However, for 1-bit and 2-bit phase variation, they have a maximum magnitude at theta equals 0, but they all taper down. In other words, we assume that the maximum magnitude at any direction is actually less than what the ERS can produce using 1 and 2-bit phase variation. So the equation should underestimate because we assume that there's more, that the energy from the ERS is actually more than what it can actually produce. So that's justified. So now, with this concluded, we can move into the second part of the thesis defense, which is the flat panel ERS implementation, which we'll call the outrigger panels. So, to recap, here are 4 cases, as I talked about in the beginning of this presentation, case A, B, C, and D. So these are the 4 outrigger panel configurations that we're going to be talking about. And so, we're going to talk about first how we're going to analyze each of these systems. So we've already talked about the nulling state. And for all the subsequent examples, we want to know the second side lobe of the modified reflector pattern in the H-plane. So now we're going to talk about the quiescent. We're going to analyze the ERS when it's the quiescent state, i.e. it's just a surface extending the original paraboloid. The maximum state, when we use a serial search algorithm to maximize the main lobe directivity, in the theta equals 0 direction or boresight. And so those quiescent and maximum cases are done to determine if the gain loss to improper collimation can be recovered. So we'll talk about it in a second. So we'll compare all of these results to the conformal ERS implementation, as we talked about before, and we'll refer to that as case 0. And going forth, we're going to assume that the rim width of the ERS panels are going to be 1.2 meters, which equates to 6 lambda. So this is actual physical width of the outrigger panels. So the first case to talk about is case A. Again, we repeated case A for the top right here. And so we have the quiescent, maximum, case 0. So why do we have quiescent and maximum? So as stated before, we want to see if the gain loss to improper collimation can be recovered. So when the ERS elements are placed on a surface that is conformal to the original paraboloid, as in for case 0, there is no improper collimation. In other words, if I fire a geometrical optics ray from the feed to the ERS elements to the focal plane, no matter what element I choose, the distance will travel will be 2f and in the same direction of collimation. So they're collimated and at the same phasing. That won't be the case. That won't be the same thing for case A because now it's a flat panel, and that flat panel now disrupts that geometry. In other words, if I fire a geometrical optics ray from the feed to the outrigger panel, it's no longer going to end up at a distance of 2f at the focal plane, nor at the same phasing for that matter, because it's a different distance. So there will be gain loss to improper collimation. And we can see that here. If we just let the case in a quiescent state where there's no reconfigurability, we see that for a 4.7% smaller area than case A, the projected area, it's 15.1% lower gain. So if the system was perfectly collimated, the difference in the gains, delta G, would be that difference in area if everything was perfectly collimated because of aperture theory. So now we attempt to maximize the main lobe directivity for case A in the maximum state, and we see that the delta G is the same as delta A, indicates that we can recover the gain loss to improper collimation. So that's good there. And the second thing of which is, with this established, we can now talk about the nulling case. So the first thing to discuss is whether or not is to determine what the differences are in the nulling state. So for the gain, half power, beam width, and side lobe level, they're all relatively, the difference between case 0 and case 0 are relatively the same. The two differences come between the peak cross-pole and the null depth. So in the peak cross-pole, we see here that case A can produce a lower cross-pole, peak cross-pole than case 0. This is unintended because the serial search algorithm only focuses on the copole, although other research, future research, can focus on the cross-pole effects of this reflector system. And the last thing of which is to discuss the null depth of the reflector system. So we see here that case A has a smaller null depth than case 0, and this is because there's more area for case 0 to send more energy to drive that deeper null. So that checks out fine. And so the next thing we want to talk about is what happens when we eliminate half the panels. So we want to see if we can do canceling with half the panels of case A. And so that gives us case B. So the panels are still attached tangent to the rim of the reflector as in case A, and now every other panel is removed. So we can do the same analysis to determine if the gain loss improper collimation can be recovered. So we look at the quiescent state. Delta A, the difference in projected area, is 13.4% lower for case B compared to case 0. And the delta G is 16.6% lower for case B compared to case 0 in the quiescent case. So now we attempt to maximize in the Borsite direction, and we see that the delta G for case B compared to case 0 in the maximum state is 13.5% lower, indicates that we can recover most of the gain loss in proper collimation. So now we can move ahead to the nulling example. So in the nulling example, we see here that I also put case A here for comparison. So compared to case A, the main lobe directivity G is a little bit smaller than case A. So, and half power beam and side lobe level are relatively the same. So the main differences come between the cross pole and the null depth, the peak cross pole rather. So we see here that the null depth for case B is not nearly as deep as case A's. And this is because case B doesn't have as many panels or surface area to reflect more energy to drive a deeper null. For that very reason, though, case B actually has a lower cross-pole, peak cross-pole in case A, because the more panels for case A can now contribute more to that cross-pole field as opposed to case B. So now this does make sense. And the next thing we want to talk about now is what happens when we orientate the panels no longer tangent to the reflector, but parallel to the aperture plane. Why do we do this? Well, when you orient the panels parallel to the aperture plane, the projected area would be larger, and presumably we would be able to have better nulling performance rather. And so that's how we arrive at case C. So case C can be conceptualized as case A, but with all the panels now oriented parallel to the aperture plane. So we can do the same analysis and look at the projected area for case C compared to case 0, which is 1.6% smaller. And the gain difference is 14.5% smaller in the case C in the quiescent case compared to case 0. But when we maximize, we see something very interesting here, is that the gain for case C compared to case 0 is minus 6.2% smaller. This indicates that we cannot recover the gain loss in proper collimation. In other words, the collimation effects are much worse in case A and B, and we cannot, with the reconfigurability, we cannot recover that. And so this improper collimation does bleed its way over to the cross pole. We see here that the peak cross pole for case C is quite a bit higher than case 0 and cases A and B. So that's one of the big drawbacks of the parallel outrigger panel implementation. And we note here that the null depth isn't nearly as low as cases A and B. We'll have a slide here in a couple seconds to show all the cases here. So as we did with case B to case A, we're going to remove half the panels for case C and arrive at case D, which would make it cheaper to produce while hopefully having this nulling performance. So the last thing we can do here is see if we can recover the gain loss in proper collimation. So we jump to the final result here. We see that the gain for case D in the maximum case is 13.0% smaller than case 0, even though the area is 11.9% smaller than case 0, which means that we can now recover the gain loss from proper collimation, as with case C. So comparing it to case C, case D has a smaller null depth than case C. This is because case C has more panels to reflect more energy in that direction of the null to drive a deeper null. And we also note that for this very reason, case D has a smaller peak crosspool than case C because there are less panels to contribute to that crosspool field. So with now the tangent to the rim Auer panel configurations and the parallel to the aperture plane parallel to the aperture plane Auer panel configurations, we can now talk about the results here. So the results here are shown on the screen here, and we have case C compared to on the left. So we see here that cases A, so we can now compare and contrast the different cases. So case A, B, C, and D. So we see here that cases C and D can now recover the gain loss from proper collimation. However, cases A and B can. And we note here that if we want the deepest null depth, we would choose case A for these system parameters. If we want the lowest peak cross-pole, we would choose case B. So this is kind of like a short compare and contrast for the different cases. And so this now concludes the second and last topic of this thesis. And now we can talk about future work. So one of the first things we can do is determine if we can attach these Auer panels to a subreflector. So Gregorian subreflector systems and among other dual reflector systems are becoming common and of interest for radio astronomers now and in the next coming years. So we want to see if we can apply these Auer panels to these more complex systems. The second of which is to configure the Auer panel system for multi-band interference mitigation. So the research considered thus far was only single band, only at one frequency. So now we want to see, can we apply this to multiple frequencies and cancel over a band of frequencies? And the last thing we want to do is determine the full wave analysis for each. We want to perform a full wave analysis for each Auer panel configuration. So we should, like was shown before with the conformal error implementation, we want to determine if the physical optics approximation for these flat panels are accurate as well. So now this concludes this thesis defense.